All right, let's get right into it. We're going to peek under the hood of a really fundamental and frankly super cool problem in robotics. How does a robot arm actually figure out how to move somewhere without, smashing into things? We're going to walk through a real-world implementation step by step to see exactly how the sausage gets made.
So right off the bat, here's the big issue. This is the thing that keeps robotics engineers up at night. On the one hand, your motion planner is working with a simplified, kind of abstract model of the world. But on the other hand, the actual robot, or in this case the simulator, is dealing with the messy, complex, real geometry. And if those two things don't match up perfectly, well, the planner might cook up a path that looks totally safe on paper, but leads to a big, crunchy collision in reality. That gap between planning and execution is where things go wrong.
So how do we solve this? We're going to follow this 5-stage pipeline. First, we'll create one unified reality that everyone agrees on. Then we'll plan a basic path. After that, we'll turn that path into a slick, efficient trajectory. Then we'll execute it with some serious precision. And stick around for the end because we're going to talk about a key lesson we learned when things didn't go as planned.
Okay, let's start with the absolute foundation of this whole thing, building that single source of truth. Seriously, if we don't get this part right, nothing else we do is going to matter.
And this, right here, this is the golden rule. It is the core idea that this whole project is built on. I mean, think about it. If your planner is looking at one set of blueprints and your controller is looking at a different set, you are just asking for trouble. It's a recipe for disaster. So they have to be looking at the exact same page.
The fix for this is actually pretty elegant. Instead of juggling two different models, we just don't. We force the planner to use the exact same geometry that the MuJoCo simulator is using for execution. That's it. No more separate collision files, no more worrying if the two models have drifted apart. So now, when the planner asks, hey, can I move here? It's asking the real world, the ground truth. And this goes for everything, the robot hitting a box, or even the robot accidentally bumping into itself.
Okay, so we've got our unified world. Planner and executor are on the same team. Now for the fun part. How do we actually find a path through this world? On to section 2.
The tool we're using for this is an algorithm called RRT star. The best way to think about it is like exploring a dark forest. It sends out feelers in random directions, building a tree of safe paths. But here's the star part, the magic bit. As it explores, it's constantly looking back at the branches it's already made and thinking, hey, wait a minute, could I connect these 2 points with a shorter, better path? So it's not just finding a path, it's constantly trying to find the best path. And of course, we're not going to lob it a softball. We've set up a pretty tricky scene here, with a bunch of obstacles just scattered on a tabletop. The robot's job is to get from its start position to a goal position without hitting anything. Let's see how it does.
And here we go. Here's what RT Star came up with. Now, to be clear, it works. It found a collision-free path. But look at that, 35 waypoints. It's kind of jagged, a little inefficient. It's like taking a whole bunch of tiny little side streets to get across town. It's a valid solution for sure, but we can do better.
And that brings us right to our next section. We've got this raw, kind of clunky path. Now we need to refine it, smooth it out, and turn it into something a real robot can actually follow, a timed trajectory.
So how do we get from 35 waypoints down to something sane? With a beautifully simple trick called shortcutting. The idea is just, what if we tried to connect 2 points on the path with a straight line? If that new line is collision-free, great, we just found a shortcut. And look at the difference it makes. It's night and day. We go from 35 waypoints all the way down to just 3. And what's really cool is that the path cost, basically how far the robot's joints have to travel, also drops significantly. Simpler and more efficient. That's a huge win.
Okay, so now we've got this lean, mean, 3-waypoint path. But it's still just a connect-the-dots puzzle, right? We need to turn it into a real, fluid motion. That's where a tool called TOPP-RA comes in. It takes our path and figures out the best way to move along it, calculating all the precise velocities and accelerations, all while making sure we don't violate the robot's physical speed limits.
And after all that planning, all that optimizing, here it is, the final number. The entire move, from start to finish, through that whole obstacle course, is going to take just about 2.7 seconds. Not bad at all.
A plan is great, but a plan is just a list of numbers until the robot actually starts moving. So now, for section 4, we have to make the robot follow our beautiful plan with extreme accuracy. Let's make it happen.
This is where the control magic happens. At every single millisecond, we're doing a few things. First, we look at our trajectory and ask, where should the robot be right now? Then we use something called a PD controller, which basically acts like a smart rubber band, to pull the robot towards that desired spot. Critically, we also add in a term to compensate for gravity. You can't forget gravity, or the arm will just sag. And finally, we make sure the commands we're sending are something the robot's actual motors can handle.
And here's the payoff. This is the mic drop moment. The final tracking error is just 0.0037 radians. I mean, to put that in perspective, that is tiny. It is incredibly close to zero. This number tells us that the real robot's motion was almost a perfect mirror of our plan. It's the proof that the whole pipeline, from top to bottom, actually works.
But, real-world engineering is never quite that clean, is it? The pipeline we have now is solid, but getting here meant hunting down a really nasty bug that almost brought the whole project to a standstill.
So here's what happened. We got our shortcutting algorithm working, and it was awesome, most of the time. But then, every once in a while, the whole program would just crash. No warning, no obvious reason. It took a ton of digging, but we finally found the culprit. Our shortcutting was so good that sometimes it would produce two waypoints that were almost identical, like ridiculously close to each other. And when we fed that list of near duplicates to the TOPP-RA library, its internal math just broke. And that's such a classic engineering problem, right? Your code works, their code works, but they just don't play nicely together.
So what do? You can't just go in and rewrite their library. Well, the fix was actually super simple and really smart. We built a little guard, a pre-filter. Before we even think about calling TOPP-RA, we just run a quick check on our list of waypoints. If any 2 points in a row are too close together, we just toss one of them out. It's a simple, defensive bit of code that makes sure the library only ever gets clean data it can handle. It's a great lesson. You can't always control the tools you use, but you can control what you feed them.
And all of this kind of brings us to a final big picture question. We just walked through this whole complex pipeline, planning, optimizing, debugging, controlling, and it works beautifully. But it does make you wonder about the trade-offs, doesn't it? In robotics, where every bit of computation can matter, how do you know when you've done enough? When does a solution cross the line from being robust and good enough to being just over-engineered? It's definitely something to think about.